NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams.
Something strange has just surfaced from the edge of the known universe. So strange, in fact, that even a Nobel Prize-winning scientist is speaking out. The James Webb Space Telescope, humanity's most powerful eye in space, has captured more than just a pretty picture. It found something that doesn't quite fit, something that wasn't supposed to be there. How could this discovery reshape our understanding of the universe's beginnings? Could it point to a missing piece in the universe's origin story? Or is it a clue that we've been looking at the cosmos the wrong way all along? Buckle up, because the further we look, the further back in time we go, and what we've just seen might not be from the past we expected. The universe through JWST's eyes. The James Webb Space Telescope, or JWST, represents the most powerful and advanced observatory humanity has ever launched, with a mission specifically tailored to explore the earliest epochs of the universe. Unlike its predecessor, the Hubble Space Telescope, which mainly captured visible and ultraviolet light, JWST is optimized for infrared observation. This is critical because as the universe expands, light from ancient galaxies stretches into longer, redder wavelengths, a phenomenon known as redshift. Infrared detection allows JWST to peer much further into the past, observing celestial objects that formed just a few 100 million years after the Big Bang, a period often referred to as the cosmic dawn. JWST's larger 6.5-meter segmented mirror and operational altitude beyond Earth's heating and luminous interference at L2 constitute the essence of JWST's ability. The telescope relies on a multi-layered sun shield, which allows the instruments to remain ultra-cold and capable of detecting faint infrared signals coming from the farthest galaxies. One of the earliest achievements under JWST is the Deep Field Image, which has shown thousands of galaxies in what was once empty space. Many of these galaxies look old and very developed, far too mature than standard cosmological models would predict at such early times. Instrumented with NIR-CAM or near-infrared camera, NIR-SPEC or near-infrared spectrograph, and MIRI or mid-infrared instrument, JWST facilitated a detailed spectroscopic analysis. These instruments allow astronomers to not just capture the beauty of distant galaxies, but they analyze light to unveil the galaxy's chemistries and star formation rates and velocities. For example, the finding of galaxies, such as JWST GS-Yazithasaro, thought to exist just 320 million years after the Big Bang, raises genuine puzzles. How can such hefty and brilliant galaxies form swiftly when the universe is young? These bewildering discoveries have provided ample ground for scientists to reconsider their time-honored beliefs about the evolution of the cosmos. The JWST has designed to reveal galaxies that appear to have turned almost all their gas into stars, which was considered impossible due to feedback mechanisms such as supernova explosions regulating star formation. If substantiated, such observations could turn the standard lambda CDM cosmological model on its head. In under a year of scientific operations, JWST has not only pushed our cosmic horizon farther away, but also transformed our understanding of the birth and development of the universe, implying that some of our most trusted theories are likely to be wrong. But what if seeing deeper into space also meant peering further back in time than ever imagined? How deep space reveals the distant past. One of the most fascinating aspects of astronomy is that observing distant objects is essentially a form of time travel. Because light travels at a finite speed, about 299,792 kilometers per second, it takes time for light from distant stars and galaxies to reach us. When astronomers use powerful telescopes like the James Webb Space Telescope, JWST, to look deep into space, they are seeing light that left those objects billions of years ago. This means that the farther we look into space, the further back in time we are observing, giving us a direct view into the universe's distant past. This principle allows astronomers to reconstruct the timeline of cosmic history. For example, by observing galaxies 10 billion light-years away, we're seeing them as they appeared 10 billion years ago, long before Earth even formed. This ability to observe different cosmic epochs is crucial to understanding how stars, galaxies, and other structures evolved. With JWST's advanced infrared capabilities, scientists can now see galaxies as they were just a few 100 million years after the Big Bang, during a period called the Cosmic Dawn, when the first stars and galaxies began to shine. Acknowledged light from different galaxies traveling for hundreds of millions of years does get stretched due to the expansion of the universe. JWST has been thought to do some time travel magic, as it could detect infrared light. Many of these early galaxies were shining down on us, with light so redshifted into the infrared that the light could not have been captured by earlier telescopes, such as Hubble. JWST's instruments, especially NIRCam and MIRI, are designed to catch this stretched light, providing astronomers the chance to examine the formation and evolution of some of the universe's earliest structures in detail never before imagined. Far from being a glorified cosmic photograph, JWST's image is an important witness to the processes that shaped an early universe. Among the most useful comparisons scientists conduct is to juxtapose galaxies from different epochs, tracing back how matter came to sculpt itself, how star formation rates changed with time, and how cosmic structures have evolved over billions of years. Very few disciplines of science have as rich a stratigraphy of time as deep space observation. Not only looking across colossal distances, the telescope is also gazing back towards the birth of everything we know, attempting to answer some great questions about its being and our fate. Early galaxies that shouldn't exist yet. One of the most astonishing discoveries made by the James Webb Space Telescope, JWST, is the detection of galaxies that appear to be far more massive, luminous, and developed than what standard cosmological models expect for their age. Some of these galaxies, such as Jade's GS Z13-0, are estimated to have existed just 320 million years after the Big Bang. According to the widely accepted Lambda CDM model, this is a period when galaxies were just beginning to form. Yet JWST has revealed systems that are already bright, star-rich, and structurally complex, a level of maturity that seems impossible within such a narrow cosmic timeframe. The standard model of galaxy formation assumes that it takes hundreds of millions of years for gas to cool, collapse, and form stars at a pace governed by feedback mechanisms like supernova explosions and stellar radiation. However, several galaxies spotted by JWST appear to have turned nearly all of their available gas into stars very quickly, bypassing those normal regulatory processes. This unexpected efficiency challenges long-held beliefs about how galaxies evolve and suggests that early cosmic conditions may have allowed for a much faster or more aggressive formation process than previously thought. Currently, astronomers are investigating possible explanations for this anomaly. One idea is that the early universe gas clouds were much denser and cooler than previously thought. Hence, gravity would have collapsed them more quickly into stars. Another such idea could be that some of these objects are, in fact, not galaxies but active galactic nuclei, or AGNs or quasars. That is, supermassive black holes that lie within galaxies emitting intense amounts of light, thereby mimicking star-rich systems. To uncover whether stars or accreting black holes are producing light, the spectroscopic instruments of the JWST will analyze chemical signatures and radiation profiles. When JWST confirms through continued observation that indeed these are mature galaxies formed within several 100 million years after the Big Bang, the consequences will be historical. This can definitively change the concepts of galaxy formation, star formation rates, or, even more radically, the actual age and expansion history of the universe. Already, some theorists have suggested that the universe is either actually older than we think, or that unknown physical processes actually speed up early structure formation. In either case, finding these impossible galaxies means a watershed for cosmology and raises fundamental questions about the early universe we considered to understand well. Clashing with the Big Bang timeline. The standard Big Bang model outlines a well-structured timeline for how the universe evolved, from a hot, dense origin 13.8 billion years ago to the formation of neutral atoms around 380,000 years later, and eventually to the development of the first stars and galaxies hundreds of millions of years after that. According to this framework, large and mature galaxies should not appear until at least 500 million to 1 billion years after the Big Bang. However, the James Webb Space Telescope, JWST, has detected galaxies that seem fully formed and surprisingly massive, just 300 to 400 million years after the universe's origin, disrupting that expected timeline. These early galaxies pose a direct challenge to our understanding of cosmic evolution. They show properties, such as brightness, mass, and structure, that are inconsistent with how quickly galaxies are expected to grow under the current lambda CDM model. Some galaxies appear to have already exhausted their gas reserves by turning nearly all of it into stars, suggesting that star formation occurred at a rate far beyond what current simulations predict. This level of efficiency contradicts the notion that early star formation was slow and limited by cooling times, feedback from stellar winds, and the availability of gas. This slippage between observations and theory has caused some scientists to, even to this day, contemplate the veracity of the Big Bang timeline itself. One conjecture is that the universe is older than 13.8 billion years, leaving ample time for these galaxies to form. Other possible solutions say either that galaxy formation was merely sped up in the early universe by something else, like cooling of gas at faster rates in denser environments, or physics yet unknown, or that perhaps an intervening factor, away from the more commonly accepted picture of early formation, is that misinterpretations of redshift data or dust-obscured AGN would alter the estimates of distance and age, even though present spectroscopic studies mostly favor the early formation view. However, whatever the cause might be, it is certainly clear that the evidence points to the possibility that our cosmological models are either still incomplete or need major changes. Scientists will have to reconsider some fundamental assumptions about the early universe, including the rate of structure formation and the environment that existed at the cosmic dawn, given that large, well-formed galaxies were spotting themselves soon after the Big Bang. With further observations from the JWST, such contradictions between theory and observation might usher in a new and improved understanding of the timeline of the universe during its infancy. Is the universe older than we thought? The accepted age of the universe, based on measurements of the cosmic microwave background, CMB, and standard cosmological models, is approximately 13.8 billion years. This estimate is rooted in observations from missions like the Planck satellite, which mapped temperature fluctuations in the CMB and helped define the universe's expansion rate and structure. However, recent data from the James Webb Space Telescope, JWST, has uncovered galaxies that appear surprisingly mature and massive at very high redshifts, corresponding to a time when the universe was less than 400 million years old. These galaxies raise a troubling possibility. Either our models of early galaxy formation are incomplete, or the universe could be older than we think. Several of the galaxies detected by JWST appear far too evolved for their age, exhibiting dense stellar populations, bright luminosities, and mature structures. Some even seem to have already converted most of their gas into stars, behavior typically not seen until much later in the universe's development. If these galaxies genuinely existed that early, and are not misidentified objects like active galactic nuclei, AGN, then the cosmic timeline needs to be stretched to accommodate their formation. This has led some astrophysicists to speculate that the current estimate of the universe's age may be underestimated, or that a significant unknown process allowed galaxies to evolve far more rapidly than previously believed. There is concurrent Hubble tension, which represents the persistent difference inferred from measurements of expansion rates from the nearby supernovae against the other set that inferred from the early universe CMB data. Should a situation arise where JWST observational work of early galaxies suggest that structure formed much faster than we would imagine, this would throw in question how we interpret expansion data, or might even suggest that we have to finish a more complex cosmic history. Some theorists even argue that we might be missing key factors regarding the role of dark energy versus time, or that there are necessary amendments to the early inflation models. Regardless, that would warrant serious consideration explanation for making way for an older or differently evolving universe. Nevertheless, in light of these intriguing implications, many respect scientists plead for restraint. Since the redshift and age estimates of these early galaxies are still in confirmation through spectroscopic work, alternative scenarios, including gravitational lensing or observational bias, have not been fully excluded from consideration. However, should JWST find more clear-cut examples of well-developed galaxies at extreme distances, then the notion that the universe is older than 13.8 billion years must be earnestly entertained. At the very least, it reinforces the idea that the early universe was much more active and much more complex than would have been imagined before. This pushes the boundaries of our comprehension of cosmic history, and the surprises don't stop there. Something even more unexpected is happening inside those early galaxies. Rethinking star formation in the early universe. Star formation in the early universe has long been thought to be a relatively gradual process, constrained by factors such as gas availability, cooling rates, and feedback mechanisms from stellar radiation and supernova explosions. Traditionally, galaxies are expected to convert only a small fraction of their gas into stars at any given time, with the rest being blown out or heated up by energetic events. However, observations from the James Webb Space Telescope, JWST, have started to upend this model. Some early galaxies discovered by JWST appear to have transformed nearly all of their available gas into stars at an astonishing pace, far beyond what standard theories of galaxy evolution would predict. This surprising efficiency in star formation challenges the foundational assumptions used in current astrophysical simulations. These simulations, which model how galaxies evolve over billions of years, typically include built-in limits based on feedback processes that prevent runaway star formation. Yet, some of the early galaxies observed by JWST defy those limits, appearing as massive, bright, and densely populated systems just a few 100 million years after the Big Bang. If these galaxies are indeed real, and not observational artifacts, they may indicate that early universe conditions allowed for far more efficient star formation than previously believed. One such explanation would be that the gas in the early universe was far denser and cooler than presumed, and it was easier for gravity to collapse cloud of hydrogen and helium into stars. It wouldn't be much difficulty. There is another theory that suggests maybe those galaxies formed in a highly compact manner. This helped them retain gas and build stars more quickly. Yet, possibly other unseen environmental factors like powerful cosmic radiation fields or different cooling pathways could have affected the progress. This said, some of the objects detected by JWST may not be galaxies rich with stars at all, but could be active galactic nuclei, AGNs, or quasars, mimicking the light signatures characteristic of stellar populations. Follow-up spectroscopics from JWST is critical to ascertain those scenarios from each other. By studying what elements and lines of emissions were observed from those galaxies, astronomers will know if the light does really come from stars or from swirling matter around a supermassive black hole. If JWST continues to attest that most of these ancient objects do indeed belong to their stars, it will be a challenge to an extensive revision of forms in which galaxies formed in the very early stages of the universe. These might reconceive star formation laws, roles about the dark matter scaffolding, and physical conditions of the cosmic dawn. The Hubble tension. The Hubble tension is one of the most pressing, unresolved problems in modern cosmology. It refers to the persistent discrepancy between two methods of measuring the Hubble constant, HU, which represents the current rate of the universe's expansion. Measurements based on the cosmic microwave background, CMB, particularly from the Planck satellite, suggest a lower value of about 67 to 69 km per second per megaparsec. In contrast, direct observations of nearby supernovae and Cepheid variable stars, led by researchers like Nobel laureate Adam Rees yield a significantly higher value of around 73 to 75 km per second per megaparsec. Despite improved precision on both sides, the gap between these values has not narrowed, suggesting a deeper issue may be at play. This tension is not a trivial disagreement. It implies that our understanding of fundamental physics or the early universe could be incomplete. The James Webb Space Telescope, JWST, has added a new layer to this mystery by revealing galaxies that appear more evolved and structured earlier in cosmic history than expected. These findings could affect the assumptions underlying distance and expansion measurements. For example, if galaxy formation occurred faster than previously thought, it might shift how we interpret light from distant sources, indirectly influencing Hubble constant calculations. Some scientists are speculating that the Hubble tension may indicate new physics that is not encompassed by the standard lambda CDM cosmological model, which includes dark energy, lambda, and cold dark matter, CDM. Among the possible solutions proposed are time-varying dark energy, modifications to gravity, or the presence of new particles that would have altered the expansion rate of the universe at some time shortly after the Big Bang. Others suggest systematic measurement errors as the source of skewed results. However, with each method becoming more refined, yet the tension persists, the chances for the phenomenon to be real and not an artifice, continue to mount. Addressing the Hubble tension, new missions such as the Nancy Grace Roman Space Telescope of NASA and ESA's Euclid satellite will fly into space to provide more accurate measurements of celestial distances and expansion across a much larger region of sky. All the while, early observations with JWST open a different window into the early universe, which might be critical in revealing how early galaxy formation deviates from CMB models. Whether it leads to new physics or improves the models, the Hubble tension represents a rare instance in science, a well-characterized, reproducible anomaly capable of shifting dramatically our understanding of the universe. Dark matter and dark energy. Dark matter and dark energy are foundational components of the standard cosmological model, yet they remain among the most mysterious elements in physics. According to the lambda CDM model, the universe is composed of approximately 68% dark energy, 27% dark matter, and only about 5% ordinary, baryonic matter. Dark matter helps explain how galaxies and clusters maintain their structure despite not having enough visible matter to account for their gravitational pull. Dark energy, on the other hand, is the hypothetical force driving the accelerated expansion of the universe, as discovered through observations of distant Type Ia supernovae in the late 1990s, work that earned scientists like Adam Rees a Nobel Prize. Despite its vital roles in the model, dark matter and dark energy have never been directly detected. Their existence is assumed in terms of gravitational effects and the influence of cosmic expansion. New observations from the James Webb Space Telescope, JWST, are beginning to set questions on how reliable the contemporary understanding of these components really is, as JWST has found very high redshift massive galaxies that seem to form only a few 100 million years after the Big Bang. Such galaxies appear much too large and evolved for the current amount of time available, assuming gradual dark matter scaffolding structures in the universe. This incongruence has given rise to the debate as to whether dark matter behaved differently in the early universe as compared to its present conception. Some physicists urge consideration of other forms of dark matter that might cluster more rapidly or inconsistently with cold dark matter. For example, warm or self-interacting dark matter is proposed. Contrariwise, an alternative revival of the mechanisms of dark energy over time is invoked by others. Should dark energy have had a different behavior in the early universe than it has at present, this would induce a different rate of structure formation, construed to assist the JWST observations without completely rejecting the standard model. Modified gravity theories have also been put forward as alternatives to dark matter, dark energy, while these generally have difficulty in explaining various observations in concert. The discordance between JWST data and current cosmological models emphasizes the necessity of further understanding these dark components. While lambda CDM still accounts for much of what we see, from the cosmic microwave background to distributions of galaxies, anomalies such as these early massive galaxies compel scientists to scrutinize their deeply held beliefs. The fact, then, that the questions that JWST raises imply that the dark sector could still hold surprises for us, surprises for which we might chalk up the answer to the discovery of new particles, modifications to the laws of physics, or tempering the behavior of dark energy and dark matter through time. Cosmic microwave background. The cosmic microwave background, or CMB, is the oldest light we can observe in the universe, a relic from approximately 380,000 years after the Big Bang. At that point, the universe had cooled enough for electrons and protons to combine into neutral atoms, allowing photons to travel freely for the first time. These photons, now stretched into microwave wavelengths by billions of years of cosmic expansion, make up the CMB. Observations from satellites like WMAP and Planck have mapped tiny fluctuations in the CMB's temperature, which represent the density differences that eventually led to the formation of galaxies and large-scale cosmic structures. The CMB has been instrumental in shaping the standard cosmological model. It provides precise measurements of key parameters, such as matter density, baryon density, and the universe's rate of expansion at early times. It also supports the theory of inflation, a rapid expansion of the universe in its first fraction of a second, which helps explain why the CMB looks nearly the same in all directions, an attribute known as large-scale isotropy. However, some subtle anomalies in the CMB, like the so-called cold spot, have led scientists to question whether there might be physics beyond the current model or even hints of a multiverse, where collisions between cosmic bubbles could leave imprints in the CMB. Even if Webb is not meant for probing the CMB directly, it serves very well as one of the major complementary instruments. Watch Hubble here as it observes galaxies born just a few 100 million years after the Big Bang, letting astronomers test the structures emerging in the universe's early years against those predicted by the CMB. A strong diversion from CMB-based models in the distribution, size, or formation rate of galaxies at high redshift might indicate that critical assumptions on the evolution of the universe would have to be revised. This connects the very first light of the cosmos to the first stars and galaxies in one vista take on cosmic history. If JWST discovers any new aspects of the universe's primitive structure, scientists are eagerly looking if they correspond with models derived from CMB data, or rather, if any newer discrepancies would arise. Any such consistent mismatches of JWST observations with CMB expectations could imply that there are missing pieces in our understanding of the early universe, involving perhaps dark matter interactions, inflationary processes, or initial conditions. By bridging the CMB era with the cosmic dawn, JWST and CMB studies are together filling out a more full, and perhaps more complicated, portrait of the universe's origins. As we connect ancient light to modern insights, a deeper question begins to surface. Is a new universe theory taking shape? With mounting evidence from the James Webb Space Telescope, JWST, revealing anomalies in early galaxy formation, many scientists are beginning to question whether the standard cosmological model, known as lambda CDM, can continue to explain the universe in its entirety. This model, which includes dark energy, lambda, cold dark matter, CDM, and the framework of the Big Bang followed by cosmic inflation, has long served as the cornerstone of modern cosmology. Yet, JWST's discovery of massive, mature galaxies existing just 300 to 400 million years after the Big Bang has placed pressure on this model, suggesting that fundamental components of our understanding may be missing or incomplete. One of the most significant implications of JWST's data is the potential need to revise or replace parts of the Big Bang timeline. The presence of galaxies that appear too evolved for their age, challenges assumptions about how quickly stars and structures can form under current physics. The possibility that these observations reflect errors in distance or mass estimates is being investigated, but if confirmed, they may indicate that galaxy formation began earlier, or proceeded faster, than our models allow. This has led theorists to explore alternative models of the universe, such as those that incorporate earlier or more efficient structure formation, or entirely new physics not included in the standard picture. Among the more radical ideas gaining traction are models based on quantum gravity, cyclical universes, or variations of cosmic inflation. Some proposals suggest the universe didn't begin with a singular Big Bang, but instead emerged from a prior state or underwent multiple expansions and contractions. Others incorporate ideas like a varying speed of light or modified gravity to account for discrepancies. Nobel laureates such as David Gross and Adam Rees have emphasized that crises in science, like the ones now emerging, often pave the way for breakthroughs that unify older theories with new insights, especially in bridging the gap between quantum mechanics and cosmic-scale physics. While none of these new models have yet unseated the standard one, unsettled observations, ranging from early galaxies to the now dominant Hubble tension, signify that cosmology is undergoing a pivotal moment. The forthcoming missions, such as ESA's Euclid and NASA's Nancy Grace Roman Space Telescope, will accumulate data to validate these inconsistencies or narrow down current theories. Either way, it looks like we are at the dawn of a new age in understanding the universe that will redefine our notions of space, time, and the origin of everything, nearly rewriting our cosmic framework. In addition, modified gravitation theories such as MOND or modified Newtonian dynamics and the emergent theory of gravity are being investigated to explain the observational phenomena. While these have often been classified as parental views, JWST observations give them a new life. We are seeing a breakdown in the expected behavior of structure formation at the earliest epochs, remarks Dr. Priyam Vada Natarajan, an astrophysicist of theoretical orientation at Yale. That demands bold thinking, even if it means reworking the very forces we thought were fundamental. Meanwhile, science philosophers and cultural scholars have begun to compare the occasion with other scientific revolutions, like that from Newtonian physics to Einsteinian relativity, reminding us that the evolution of science happens not only through answers, but also through questioning the foundations we so often take for granted. Thanks for watching. If you found this as fascinating as we did, don't forget to like the video, subscribe for more mind-blowing space discoveries, and drop a comment below. We'd love to hear your thoughts. Ready to go deeper? Click the next video on your screen and continue the journey into the unknown. See you there.